Hi everyone, good day and welcome to our AB 106 class for the properties of AB materials. So good day once again, and this lecture video is prepared for the lesson number 4, which is the color and dielectric or electromagnetic properties of AB materials. So the last time we have discussed about the physical, the frictional characteristics, including the frictional characteristics, physical characteristics of agricultural and biological products. So this time we will move on with our next topic, which is the color and electromagnetic or dielectric properties of agricultural and biological products. So allow me to share with you my presentation. Okay, so for this uh, lecture, I will be presenting the various color and electromagnetic properties of AB materials. So when we say color, those are properties that can be visible to the eyes, or properties that involve lightness, yellowness, or any color values of the product, including chroma, hue, or the range between greenness to redness, yellowness to greenness, and so on. So specifically, the color properties of agricultural and biological materials can also be measured using the different reference or instrumental measurements. It can also be assessed using the advanced technological or advanced techniques, including image processing and like hyperspectral image characteristics of the product. But anyway, somehow, the most common or traditional way of measuring the color values of the food products are done using instrumental methods. Okay. The objectives of this lecture, first one is to discuss mainly the importance of color and the electric properties of AB materials, as I have mentioned a while ago. The second one is to discuss the interaction between the AB and materials and color and electromagnetic energy, the principles behind, the theory behind color and electromagnetic properties of various products. Identify some applications of color and dielectric properties of AB materials. Where are they applied? How useful are they? Why we need to study these properties in food or agricultural processing. So we need to discuss this, and then later we will know how or what is the importance of color and electromagnetic properties. And we will solve problems related to these properties. You are then expected after learning or after this lecture, you are expected to know the importance of color and the electric properties. And you can then explain what are the relationships, or what are the difference between the electromagnetic and color values, and relate some applications or its usefulness in the food processing or in the agricultural sector. Okay, by definition, accordingly, color is an important physical property which determines the acceptance of a food by consumer. Okay, a variety of systems have been developed to describe colors. Color order systems. Okay, the color order systems are three-dimensional arrangements of color according to appearance. So when you say three-dimensional, so we have to review our physics based on the three-dimensional or the XYZ. Okay, so we have the X, the axis, the Y axis, and the Z axis, wherein we can get the color arrangement or the interaction as a factor or as a result of the light interaction. Okay, that's the color order systems. The selective absorption of different amounts of wavelengths within the visible region determines the color of a food material. Okay, so if you can visualize or if you can picture out, you have a certain material and then there's a light or presence of light, and then that presence of light could have an impact or effect to the color of the material or the food product. And then when you get the value or the color value of the product, so you have to set white as your reference color, and then you can get the color values in terms of lightness or hue, chroma, or whatever. Okay. Dielectric properties of foods are also important. Okay. When you say dielectric properties, those are the related to the electromagnetic or to the, from the terms electricity, electron. So those properties that are related to the electromagnetic or electric properties of the food products. Okay, so they can also be used in assessment of food quality. The dielectric properties are the dielectric constant and dielectric loss factor. As you can see on the picture, there's a dielectric constant that you can see as it transmits to or separates from a material or plate. So it is the ability, the dielectric constant is the ability of the material to store microwave energy and dielectric loss factor. So the dielectric loss factor is the ability of a material to dissipate microwave energy into heat. Dielectric properties are functions of moisture content, temperature, and composition of the material. So the dielectric properties are the result of the moisture content, temperature, and composition of the material. So when you have to study, for example, the quality of the food material, you can relate the changes or the variations in the moisture content, temperature, and other compositions of the food product based on the dielectric properties of that particular product. As you can see on the picture, there is an electromagnetic spectrum as differentiated in terms of its frequencies. So you can see that when the electromagnetic radiations strike an object, the resulting interaction is affected by the properties of an object such as color, physical damage, presence of foreign material, and other quality factors such as like defects, deformations of the product, and any obvious changes on the product, which you can see on the surface or on the physical appearance of the product. So any changes of that can also change the electromagnetic characteristics of that particular product. So different types of electromagnetic radiation can be used for quality control of foods, because as the quality of the food product changes or the quality of the food products vary, there's a variation of the quality attributes of the food products, the electromagnetic characteristics also changes. So there's a relationship between that. And then you can analyze, or you can conclude that as these particular characteristics changes, this also quality attributes or characteristics also changes. So there is a relationship between the two. Electromagnetic radiation is transmitted in the form of waves. As a review on our physics class, okay, we can classify into wavelength and frequency. The electromagnetic radiation spectrum, we can classify into wavelength and frequency. Okay, the waves travel at the speed of light, which is measured into frequency, and the wavelength, lambda, and a medium, when these two properties are related as equated, or as can be defined as C is equals the lambda or the wavelength times the frequency F. Then that's the value of electromagnetic waves. Where C is the speed of light in a vacuum, 3 times 10 to the power of 8 meter per second. So it's a constant value of C. Basically, radiation can exhibit properties of both waves and particles. Okay, visible light acts as if it is carried in discrete units called photons. Okay, each photon has an energy E that can be calculated by the formula or equation E is equals h times f, where h is the Planck's constant and f is the frequency of that certain wavelength. When radiation of a specific wavelength strikes an object, it may be reflected, transmitted, or absorbed. Okay, that transmission, reflection, or absorption, you can get that characteristics to relate also the changes or the quality changes of particular food products. So it's very useful to know the basic criteria, the basic principles behind absorption, reflection, and transmission of the light, okay, or radiation to the food product. So that's how it is related. And why we need to study electromagnetic light interaction from the light itself to the food products? How are they related? What's the importance? Okay, that's the main goal. Because from the light interaction, and then you get the light characteristics of that particular product, and then you can then relate what's the maybe the might as well we can get the uh, quality values or quality characteristics of that particular product based on its light characteristics. It's either it's from its photons or from its a result of its scattering and absorption, reflection of the light against the sample. So we can get that for our analysis or any interventions or any studies related to the quality of the product. So there are different types of reflection. We have diffuse, we also have specular, and we also have we only have two types of reflection. We have diffuse and specular reflection. So diffuse reflection happened when a surface is rough, the incident light will bounce around. So it will just bounce around like uh, a representation of like an interaction between the light between the light and the material, and then the light will just comes back, or we just it's a contrast from its original. So it's a diffuse reflection. When you see specular reflection, there's an angle equal to the incidence of the radiation beam. Okay, so the angle of reflection, there's an angle occurred, there's an angle formed based on the interaction of light. Okay, so that's how the diffuse and the specular reflection varies or differs. Also, there are two types of transmission. So again, the most common characteristics of light interaction, we have diffusion, transmission, and absorption. Also have reflection, absorption, and transmission. So for the transmission, we have two types. Okay, so we have diffuse and rectilinear. Okay, diffuse transmission is similar with the reflection, wherein we can see bouncing interaction of light. Same goes with diffuse transmission. However, for the rectilinear transmission, it's like concentrated light passing through a medium or through an object without reflection that happens or occurs, right? No bouncing, but it will emit, it will pass through an object. Okay, for example, it's from the bottom to the top. So with the internal characteristics, it will surpass or it will pass through that particular sample or object. Okay, so specifically for color, so we'll continue with the color properties, the basics or the theory behind color. As defined, color is one of the most important quality attributes in foods. Okay? It is one. Why it is one of the most important quality of foods? For example, when you buy or when you select a product, agricultural product, it's either a fruit or fresh harvest product. You have to judge or prejudge that particular product based on its physical appearance, as I have mentioned during the physical properties. And then after that, you will check if, okay, the size, the shape is okay. There's no defects. There's no deformations with this product. And then the next one, you have to check if the color is okay. If it meets with your standard, like this must be color yellow if this is ripe banana. This must be color yellow if this is ripe like orange. This is color orange if this is a ripe orange. This is color green if this is a ripe like this, like that. So you will always check. You will always refer. You will always look for the color, the right color of the particular product, right? So this is one of the most important attributes that most consumers will really check or rely on before purchasing or buying that particular product. And it will follow based on the necessary uh, characteristics also, like flavor, functional values, uh, size, shape, the taste. So it will then follow. I mean, first you have to see or look for the physical appearance, and then after that you will check the taste, the aroma, its content or whatever. If it's too acidic, it's too sweet or whatever. So everything will follow after getting or after assessing the product based on its color characteristics, right? So you need to measure the color. No need to measure the color if you are in the supermarket, because color, maybe, although it is one of the most important characteristics, but you don't have to measure the color just to see if its quality is good or not, right? Because most sorting machines or food processors will identify or classify or sort that particular product based on its quality standard. So this color, it belongs to the ripened ones. This color belongs to the fresh harvested one. This one belongs to the unripened group. Okay, or unripe groups. So anyway, for the technical quality evaluation, you really need to measure the color. Okay, so the color measurement may be used if correlation is present between the presence of the colored component and the chemical in the food, since color measurement is simpler and thicker than chemical analysis. Why? Because when you measure the color, you just use instrumental measurements, and then you put uh, uh, or you measure against the peel or the husk of that particular food product or material or sample, and then you can get the color values in terms of lightness, chroma, hue, whatever, and then you can correlate in terms or against its internal properties, like its moisture content, soluble solid content, uh, what acidity or whatever. So color can be correlated with the other internal characteristics of the food materials, because color is external characteristics. Color is a perceptual phenomenon that depends on the observer and the conditions in which the color is observed. Why it is perceptual? Because somehow you can see that the color is good, but the taste is not, right? Okay, for example, you went to a supermarket, and then you see that okay, this looks fresh based on the color, but when you taste, it looks it tastes like deteriorated. It tastes like overripe product. So it might be on the perceptual or perceptual aspect, but somehow color can also be the most good indicators of the quality, right? Because when you say, for example, oh, it looks overripe, and then there's some defects, and then the natural color of that particular product is, for example, the natural color of that particular product is yellow when it ripens, and then you see that it's like already color semi-brown, yellow with semi-brown, so it's no longer a good quality, belongs to a good quality product. So based on color, you can then assess that it's not a good product already. So color can be a good judgment on the quality of the food product. Okay, and then it may be desirable to follow the changes in color of a product during storage. That's just same on similar with my statement, right? That for example, maturation, also processing, drying. As the color changes, you already know that the quality also changes. Okay, even if you don't have that particular data, but you can already say that as the color changes, there is corresponding change or corresponding effect on the quality of that particular product. Okay? Physically, the color of an object is measured and represented by spectrophotometric curves. Okay? There is a curve or changes on the wavelength or characteristics of that product. And then it will then define how the lightness or what's the value of the lightness, the yellowness, color of the product, the chroma, the hue, or etc. Okay? And an object, a light source, for example, when it reflects to the material, okay, for example, on the picture as shown, when the light or any light source illuminates or reflects on the food material, as an observer, you can also see that there's interaction, right? But beyond the naked eyes, you cannot see that there's a strong like absorption or reflection or whatever that changes or occurs on that particular situation. So you need instrumental measurements. You need high technology or advanced technology to measure the minute or even the single interaction for that particular activity, right? So you need to that. However, the light is the main source or is the main illuminant for measuring the characteristics of the food, color characteristics of the material. Even the instrumental measurement, when you use instrumental measurement like colorimeter, when you put the colorimeter below the product or beneath the product, it will flash first, it will give light before it will read the color characteristics of the product. So the light is the main source for getting the color values of the food product. A light source can be turned on and off and can be used to view an object. An illuminant, on the other hand, is a mathematical description of a light source. For detection of differences in color under diffuse illumination, both natural light and artificial simulated daylight are commonly used. However, natural daylight varies greatly in spectral quality with direction of view, time of day and year, weather and geographical location. Okay, as mentioned, the natural daylight or artificial simulated daylight, what's the difference? When you say natural daylight, it's the natural daylight outside the room, outside the house, natural given by the nature, like the sunlight. Okay, so artificial simulated daylight are, for example, lamps, okay, like the fluorescent lamps, bulbs, which gives us a light, artificial light. So it can still give us color characteristics of the product based on the interaction. Okay. However, accordingly, natural daylight varies greatly. Okay, it varies greatly. Maybe that particular day it's quite dim. That particular day is too light. The light is too heavy or too much for that particular testing, because as the time or the for example, on the morning or on the morning that the light might be not saturated, but at the afternoon the natural light might be too saturated. So that's how the natural light that's how the disadvantage of natural light. For the artificial light like fluorescent bulbs or lamps, it will give you a constant light effect, right? Except only if that particular light bulb or lamp is quite deteriorated, or the span or the years of that particular lamp is already like more than 10 years. So it will give you a dimmer light characteristics or light effect. Okay. So by that, the Commission Internationale the Éclairage or Commission on Illumination recommended 3 light sources reproducible in the laboratory in 1931. Why? Because that time, if they will use daylight as their main source to get the value or the reference value of the particular product, color values of the particular product, they might have or might as well, they got varied results because as I have mentioned, daylight is not that much will give constant or uniform light effect. So by that, they set a standard to make or to have a reference light source for measuring the color values of the object. Okay, so they called it 3 illuminants. So illuminant A, illuminant B, and illuminant C. So that's the proposed or the standard based on the CIA. For illuminant A, it will define light typical of that from an incandescent lamp. Okay, so they base that from the incandescent lamp, the illuminant A, because when you measure the color characteristics of the food product or object, you really have to have a calibrated or standard color which is white, just like the fluorescent. Okay, just like the daylight. However, for the daylight, it may changes, like it may somehow like color yellow. Okay, it may somehow like a hazy color. Okay, or like almost orange color. So it is not uniform. Then that's why the CIA decided to just have a standard color illuminant. So let A will define like similar with incandescent lamp. For the B illuminants, it represents direct sunlight. Okay, direct sunlight. Okay, but they did not say that. For example, they did not say that that illuminant is direct sunlight in the morning or direct sunlight in the evening, or I mean, sorry, in the afternoon. They just stay in general or specific that direct sunlight. And illuminant C represents average daylight from the total sky. Okay, so they got the average illuminance, okay, from the daylight sky, because as we can review or remember, the sunlight effect or the power effect from the ground versus from the sky or atmosphere is different. So maybe somehow, or might as well, this was the basis of their reference. Okay, so again, there are 3 illuminants set by CIA. The first one is based on a typical incandescent lamp. The other one is based on the direct sunlight. And the other one is based on the daylight from the sky. Okay. Then, based on measurements of daylight, okay, CIA recommended a series of illuminants D in 1966 to represent daylight. Okay, so they focus on the daylight and then it becomes illuminant D. These illuminants represent daylight more completely and accurately than illuminants B and C. Okay, so after a series of data gathering, series of research, series of evaluation, they have found that illuminant D, okay, they have found that the daylight is a good standard or reference for that color measurement. So they call it illuminant D. Okay, color measuring instruments are categorized into 2 types. Okay, we have spectrophotometers and colorimeters. Okay, after a series of researches, after a series of development, innovation from this CIA, and then now we have the available color measurement instruments, which are categorized based on spectrophotometers and colorimeters. When we say spectrophotometers, these are instruments or color measurement instruments which projects the red, green, or blue filters. Okay? The so-called red, green, and blue characteristics, the RGB characteristics of the material. Okay? This is how the spectrophotometers looks like. The red, green, or blue light are focused on a screen such that they overlap a circle. Okay. For example, there's the material and then there's a circular testing equipment. It's called spectrophotometers. When you get this, when you put the sample and then the light flashes, Okay, the spectrophotometers splashes, and then it will only get the value of the red, green, and blue. Okay, red, green, and blue. Why only red, green, and blue? Because in all color types, or in all kinds of color, only the red, green, and blue are the most saturated, that is related to the other color kinds. Okay, the red is similar with the orange. The green is similar with the similar with the other colors like yellow, green, or whatever. And then the blue is similar with like violet or the other colors. So the most common, based on, because it's not easy to get all the color values. So that's why the CIA just focus on the RGB, and then you will just get the redness to greenness, greenness to yellowness, redness to greenness value. So that's how the color characteristics now can be measured. Okay. The other half is illuminated by another projector or by spectrally pure light from a prism or graphting. So the light will still flash, and then you can get the RGB or the red, green, blue characteristics. The observer can see both valves of the circle on the screen simultaneously. So if you are the observer, you are the researcher. After putting the sample, close the door for that spectrophotometers, and then you say, for example, you select read or measure, and then you can see how the measurement happens inside. So basically, the principle of spectrophotometers is equipped with rheostat, okay, to vary the amount of light from each of the red, green, and blue sources. So there's a rheostat, like it's a flashing rheostat, and then it will differentiate. It will get the characteristics of red, green, and blue. Okay, the observer can determine the amounts of red, green, and blue required to match almost any spectral color by varying the amount of light. Spectral color can be defined in terms of the amounts of red, green, and blue, balik-balik, based on Francis 1983. So the most common is the red, green, and blue. However, colorimeters, on the other hand, before the 1950s, okay, very quite late than the spectrophotometers, it will calculate the X, Y, and Z section, or the X, Y, and Z part, or X, Y, and Z, like it's a section, or for example, in your XYZ rule in your physics or mathematics. Okay, the X value represents for the, for example, the X value represents for the vertical, the Y value represents for the horizontal, the Z value represents for the other portion. Okay, so for the colorimeters, it will also measure the X, Y, and Z section of that particular product, and then for the X, it will get the color characteristics, and Y and Z, and then the averaging method. Okay, the tres-stimulus colorimeters, which are available or commonly used colorimeters nowadays, were developed since spectrophotometer integration was expensive. Okay, so colorimeters are a result of the development or comparative analysis or studies on the spectrophotometers. So they have innovated, they have invented colorimeters, because colorimeters was spectrophotometers maybe were quite expensive. This is how this colorimeters, handheld colorimeters, looks like. Okay, so I have used this during my thesis before, my master's thesis before. This is the handheld colorimeter. So if you can see on the picture, when you get the value or the color value of the product, there's a flash or illumination first. It will flash before giving you the values in terms of L, A, B, U, and chroma. Okay, the L represents for the lightness, the A represents for the redness to greenness, the B represents for the yellowness to greenness, and the H represents for the U, and the C represents for the chroma. Okay, and then after, for example, based on the picture, after getting the value of that color value for that part of the sample, you need to get to to get the other color values of the other side, and then the other side, and then you get the average. Okay, and then you have to calibrate again the colorimeter on a white cloth or in a white paper to get the reference, or the when you to get or to calibrate the measurement characteristics of this color measurement. Okay, there are also color order systems. So the first one, we have Munsell color system. So in the Munsell, which was developed by American artist and teacher Albert Munsell in 1998, we can see that there's like sectioning, or there's a partitioning of the colors. Okay, so it's quite difficult to identify if you will get manually based on the grouping, or based on the visualization. So thousands of colors can be described by using hue, value, and chroma, right? Very difficult for this color system. Hue is a quality by which one color is distinguished from another. For example, you have to capture or measure the color green, and then color yellow green, and then you can get the hue or the difference from the green on the color yellow green. Okay, so maybe the hue is the yellow value because it differs based on the yellow, green, and the green. Okay, so hue is the quality by which one color is distinguished from another. The Munsell color system also measures chroma other than hue. Chroma, on the other hand, is the quality that distinguishes a pure hue from a gray shade, right? A pure hue from a gray shade. So for example, again, you measure color yellow-green, and then you measure color green, you get the hue value, and then that hue value can also be differed, or can also be identified from the grayscale standard, and then you can get, that's the chroma value. Okay, so chroma is based on the grayscale value, while hue is measuring the difference from one color to the other color. In the Munsell system, chroma is defined by 10 or more steps, up to 16 steps. In the radial direction, it is a measure of the difference from a gray of the same lightness. So I just want to emphasize how the hue and the chroma differs. For example, again, you measure color green versus color green. Okay, there's no hue for that, no hue value. It will give you 0 hue. Why? Because it's the same color. Okay, unless otherwise, if the other green is a varied color green, like there's a dot, or there's some part that it's quite yellow green. But if you measure the same color, red versus red, and then you have the same color material, or printed material, which is color red, and then you cannot get a color hue. Okay? You cannot get a value or a characteristic that is or a hue characteristics, because it's the same color. But somehow you can get, for example, red versus red. Okay, red versus red. But those samples were printed on a different printer, or those color samples were made from a different cloth, and then you can get hue value. You can also get the chroma value based on the standard grayscale. Okay, so that's how the hue and the chroma can be measured. The other color order system, we have CIA system, okay, or the Scilab system, CIA system, okay? One of the well-known systems to describe colors is the CIA color system developed by the International Commission on Illumination in 1931. This is a trichromatic system that is any color can be matched by a suitable mix of the 3 primary colors, red, green, and blue, okay? We have 3 primary colors, red, green, and blue, but we can still get the difference from the red, green, and blue, or from the red versus yellow, red versus orange. We can get that in the way of CIA system, where XYZ characteristics or XYZ portioning are measured. Okay, the system uses the chromaticity diagram to designate various colors. So see, we can see the chromaticity diagram, how it is being grouped, okay, according to the color grouping, or based on the primary colors, red, green, and blue. Okay, so that's the CIA system. When determining the specification for a color, the reflectance and transmittance at each wavelength are measured. These values are weighted by functions that represent the relative intensities of reflectance on the corresponding red, green, and blue. Okay, so the difference between Munsell system and the CIA system is that in the Munsell system, you can get the color characteristics based on the primary red, green, and blue, based on its chroma and hue, right? Again, in chroma and hue. But for the CIA system, you can get the color characteristics based again on the primary colors red, green, and blue, but on the XYZ grouping, wherein you see, okay, you see a grouping based on chromaticity diagram. That's how the differs. The last one, I mean, the measurement, the calculation for the CIA is just, you just have to get the like proportion or the magnitude of the XYZ color with respect to the X. And then you get the magnitude of, the average, the sum, sorry, sum, not magnitude. The sum of XYZ axis or characteristics, get the XYZ, and then when it terms in terms of X, and then for the Y characteristics or Y axis, just get the average, and then in terms of Y, it is Y over the sum of the XYZ. Same goes with the Z. You just get the reference in terms of Z divided by the sum of XYZ. So that's how it is calculated respectively. The other one, we have CIA lab system. Okay, it is called so-called Scilab color measurement. This is a method wherein it offers more advantages, or it's easier to use or to measure than the other two color systems. Okay, this was developed or firstly used in 1976 after the series of innovations or development starting 1931. Okay, so the Scilab system, it will locate the L, A, and B color values directly. Okay, what's the L? So the L represents the difference between the light from 100% and dark. Okay, so the lightness is, for example, you have incandescent lamp, which is very white color, and then that is the most that is the reference color. For example, the perfect color or the clearest color is 100%, but it dims dimmer, it becomes dimmer, so it becomes less than 100. So that's the lightness value, right? For example, maingon mo nga, as grabe kahayag ang suga kay bag-o pa. So we can say that maybe the lightness is equal to 100%. But after how many months, the lightness will deteriorate as the product deteriorates as well, right? Maybe the maximum lightness is just equal to 80 after 3 months. So in the Scilab system, ang lightness, sukdo niya ang ka-lightness value sa, for example, color green. Sukdo nimo ang color green. The lightness value of that green is only 92. So di siya perfect na green. Kaya 92% raman, 92 raman ang iyang lightness. Okay? You measure color red. Okay. Grabe man ni ka red. Oy, sukdon daw nako gamit ang colorimeters. Pag tanaw nimo dito sa result sa colorimeters, ay green ang value is 78 raman ang L niya. Meaning, it's not a perfect green, no? Based on its standard lightness para sa green. Okay? So, nagets ba? So, ang kalahian sa Munsell, Sci, o Scilab, okay, or CIA and CIA lab, is that they will measure the reference primary colors RGB, red, green, blue. However, their measurement methods are different, no? Pag abot na sa CIA or the Scilab, lightness and then greenness to redness o yellowness to blueness ng iyang sukdon. Okay? Kibali murag ang saturation sa color ang iyang sukdon. So, the Scilab system, which is the most popular, commonly used color measurement system, is can be measured using the handheld colorimeters. So, automatic na si handheld colorimeters mo measure kang L, A, and B values. Okay? So, si Scilab, once again, L represents from the saturation of lightness. A represents the saturation from green to red. Okay? The difference between green to red, or ang lightness characteristic ana nila, no? Saturation nila ana kanang green up to red. So that's A asterisk. Ang B asterisk pod na component, sukdon po niya ang difference or saturation or lightness value between blue to yellow. Okay? Murag ang iyang kasaturated ba kapag ka yellow, and then against color blue. Okay? Ang iyang pagka-saturated gikan sa color white hangtod sa dark. Okay? So mao na siya ang sa L. Okay, I hope you have understood or you have you can now differentiate the three color systems. But the most commonly one is color Scilab system, color order system in terms of Scilab system. So the L and A and B are known, or coordinates are known, and the color or color characteristics of the products can now be measured. So unsaon pa siya pagsukod, sir? For example, as you can see on the picture, unsaon pagsukod sa lightness, sir? Sa A asterisk or A component, B component. Okay? L asterisk is called L component, A asterisk is A component, and B asterisk is B component. Okay? Again, L component measures the saturation or the lightness from very white up to dark. A is from the red to red and green, and the other one is blue and yellow. Okay? So saan siya pagsukod, sir? Okay? Mathematically, chroma and hue angle are defined as, sama siya ang chroma, kani nga value. It is an arctangent of hue, ang hue is an arctangent of A and B. Okay? So sa kani ang A asterisk or A component. So ang arctangent ra di ay sa imong B and A component, ang value na nimo sa U. Okay? However, ang chroma pod, ang chroma po di ay is unsa man? Unsa man ni siya? Square root sa A and B. Okay? Square root sa square sa A and B. Okay? So square root sa A and B. So ingana ra siya pagkuha sa imong C. For example, ang atong solbon is mano-mano. Okay? For example, tagaan na mo value sa L, A, and B. And then ipakuha na ko sa inyo ang chroma of U. And then you can get based on the formula. But somehow, you can just measure the color values of the food products using handheld colorimeter. And then si handheld colorimeter mo, identify na siya, mo measure na siya. Muhatag na siya og L, A, B, C, H na value. Okay? So the Handheld color space na apunta ikaupat will measure based on L, A, and B again. But ang iyang pagka-solve is quite different from the Scilab system. Okay? Nag-follow po siya sa diagram na pagka-separate sa red, green, blue, or black, and yellow. Pero somehow, the same na siya nga aspects. You can get, for example, calculate the L, A, and B value of this coat using this particular characteristic. So you can get if Y represents 4, the Y coordinates, and then the X coordinates, and the Z coordinates. So ingana na siya, guys, ang pagka-solve. Color differences. Unsa may pasabot sa color differences? Okay? Or gradient, color changes. Ang Scilab, usually ginagamit siya para sa color differences. Why? Because Scilab will measure everything. Okay? Why? Scilab will measure everything. The L, the A, the B, and the C and the H, right? Sukdod na ni Scilab. So makuha ni Scilab measurement or CIA lab measurement ang difference or delta E. Okay, yung sa pag-solve. Okay. For the delta E or color change, color difference, imo na kuhaon ang square root sa iyang difference. For example, the lightness value is, initial lightness value is 25. After 3 days, the lightness value changes into 30. So, 30 minus 25, that's the color difference for L. For the A component, it changes after 3 days like 20, and then it changes into 15. So there's a 5 difference, and so on and so on. And then you can get the magnitude or the square root. Then you can get the difference of L, A, and B. Or you can also use this formula, which is just a summary, or which just an equivalent formula for formula equation A or formula A. So the same, you can just get the same value, because why? For this formula, for this the right side formula, this is just the delta L, or the change L is just the same with this one, which is L asterisk minus L0 asterisk. So this one is just the difference. The other one is already the value of that difference. So the same equation. Okay, wherein the delta L or the delta lightness is the lightness difference from the sample to the standard. What is the standard? Okay, for example, the standard for L is 100. So what is your measurement? 78. So 100 minus 78 is you have 22 difference. Okay. For the A component, you have a difference of 25. So you just input the value and then get the 25, and so on and so on. Okay. That's how the color difference can be measured. Same with L, C, and H. So the L, C, and H coordinates or components, you can just measure as well, and so on. So this is how the color difference are measured. So for example, the colorimetric properties of potato slices during microwave frying in sunflower oil are studied in terms of CIA scale. As a standard, a BeSO4 or what is this? BeSO4, it's a sulfate plate with L, A, and B values. This is values, measured values. Equal to 96.9 for L, 7.2 for A, and what is for the B? I mean, for the L, the value is 96.9. For the A, the value is 0. For the B component, the value is 7.2. Okay? And based on the table, there is a standard value. Okay? And the question or the problem is to determine the reference. I mean the change color. So as you can see, there's a standard and there is a color values. And then how to measure? First, what is the L of the sample and the L at the standard of L? Okay, so the standard is the standard is 96.9, right, for the L. So the measured value is 69.63. So 69.63 minus 96.9 square. And sir, negative man sir, kay mas dako si measured kaysa kang standard. Don't worry, because kuha na siya, i-square pa man nimo siya based on the formula, so you can still get a positive change, no? Or a positive change in color or a difference in color. For the A component, pila man ang value sa sample, di ba, naa kay 0.567 minus 0 nga standard, so square mo na imong value. For the B, 39.2 minus the standard, which is equal to 7.2 square, mo na yung value nimo sa B. That's for frying time at under 2 minutes. And then the same with the 2.5 minutes and 3 minutes. You just have to deduct, or you just have to subtract the value of the measurement value minus the standard value. So that's how you can get the color change. So by that, mao ni ang atong answers. So for the change in color or the color change in based on L, A, and B, so naa kay 42.05. Okay? Same method for the other frying times, and the calculated E values are given in table. So this answer, 42.05, is good for the first frying time, which is 2 minutes. So you can measure, or you can solve the other frying times, this one, 2.5 and 3 minutes frying times, with the same sample here in for the 2 minutes frying time. So ang iya dayang measurement is nakatabulate diri So naa kay negative 27.27 para sa L sa 2 minutes, and then negative 29.43 sa 2.5, and so on and so on. And then the delta E is the change corresponding to all the colors, or the sum of the all changes L, A, and B. So yung lang nimo siya pag solve. Another example, the upper, middle, and lower points of birangan banana were randomly selected in order to obtain the mean color value for the measurement of the ripening stages of the fruit. Color parameters were expressed based on the Scilab system with reference to illuminant D65 and a visual angle of 45 degrees. The L, A, and B components were standardized, meaning standard sa L is 75, A 15, and B is 40, using a reference cloth. Compute for the delta A in each of the ripening stages of the fruit using the actual measurement data listed in Table 1. For example, this is your data in Table 1. Ripening stage 2, 3, 4, 5, 6, 7. So naa kay unom ka ripening stages. Kuhaon nimo si change in L, A, and B. Okay? You have to measure change in L, A, and B for all of these ripening stages. So, yun na naman kayo standard, 75, 15, and 40, i-minus lang na nimo sila sa kanang imong mga na-measure. Okay? So, unsay gibuhat? So, 75, 15, and 40 ang imong standard, right? So, measureon lang na nimo sila based ato. So, naana di ay kay, this is just a tabulated, kibali, direct na nila ako nga measurement. You just review, okay? You just review. So, 55 minus 75, mao ni siya imong value. Okay, 55 minus 75.20 55.22 minus 75, negative 19.78. And then 66.84 minus 75, kani 71.19 minus 75, negative 3.81. Same with A, pero ang standard nimo sa A is 15. Ang standard nimo sa B is 40. So you can get the difference. Unsaon na nimo pagkuha ang danan delta A? So ang delta A is negative 19.78 square plus negative 28.87 square plus negative 4.5 square, and then square root ana, mao na imong delta A. So you try to solve this at home if ang imong value are the same or correct. Okay? So gihatag na nako diri ang changes para sa L, change para sa A, and change para sa B. What you are going to measure is pila di ay ang iyang delta A sa tanan color values based on the formula ani na diri sa solution identified as B. So you try to solve this at home, okay? So let's move on with dielectric. Dielectric is the most important, is also one of the most important characteristics in identifying or quantifying the quality of the product. However, it is on the basis on the frequencies, no, in terms of hertz or megahertz of the characteristics. So we have dielectric properties, which is categorized into constant and loss factor. Okay, so it is given on the heat generation per unit volume, right, as given on the equation or the formula, where F is the frequency. Okay, and the dielectric constant times the dielectric loss factor. So that's how the dielectric properties are measured. We can also measure the power generation or power penetration depth of the dielectric properties using this equation. Okay, as can be seen in the figure here, dielectric properties of cooking oil are very low because of its non-polar characteristics. So you can see that the cooking oil is not that much high in terms of dielectric constant because of its specific gravity. So ang distilled water, because the specific gravity of distilled water is almost 1,000 liter is the density is water is equal, example 1,000 kilogram per cubic meter divided by the standard density, which is 1,000 na naka-specific gravity ng 1. So it affects, the specific gravity affects the dielectric properties of the material. So that's how the dielectric characteristics is being classified or being identified. That is why the foods depend on the moisture content because of its water content, temperature, and compositional properties. So as the moisture content maybe somehow increases or decreases, the dielectric properties also changes. Okay, so for example, estimate the penetration depth of a chicken meat during processing in home type microwave oven. Chicken meat has a dielectric constant of 53.2 and dielectric loss factor of 18.1. Assume that the dielectric properties are constant during heating. So using the formula, you can get, based on the 2,450 megahertz, which is the available microwave oven, okay, you review if what is the standard hertz or frequency of the micro oven in the Philippines. Okay, and then based on that standard microwave oven frequency, you can get the value of, okay, you can get the penetration depth, which is equal to 0.00794 meter using the formula. Okay, for your assignment, you have to read these two published articles of mine. Okay, these are two published articles which work on the characteristics, quality characteristics of sweet potatoes. Okay, what will you do? You read the following published articles working on the quality evaluation, which are specific to physicochemical, particularly color, of sweet potatoes during storage. You refer to the color measurements of these published articles, and then you compute for the change in color after storage in terms of its L, A, and B components. You assume that the standard reference value for L is 75, the standard reference value for A is 20, and the standard reference value for B is 30. Assuming that those are your standard reference values in terms of L, A, and B. And then you can see on this article the tabulated data of the measured L, A, and B. And then you get the color difference in all storage temperatures and all varieties of sweet potatoes. Okay, so that is for your assignment. These two papers, the articles or the full papers of these, the reference paper of these, will be posted at the LMS. So you just download or you just view this article, and then you refer to table 1. Okay, so for example, this one this is the article. You refer to the table of this article, this one. Okay, there's a table, and then in the table you focus mainly on the color values L, A, and B. Okay, same with the other article. You refer to the color L, A, and B. This one, table 1, L, A, and B, and then you measure the color difference based on the standard reference that I have given. Okay, so for your assignment, you do it, you measure by your own, and then you solve, calculate by your own, and then you submit at the submission button or submission portion at the LMS. Okay, so I think that's all for this lecture, which is the color and dielectric properties of agricultural and food materials. So I hope you gain knowledge, or you learn a lot, or you learn something new on the color measurements, on the color characteristics of agricultural and food products. And then you review, you answer the assignment so that you will be guided, or you can master how to manually compute the L, A, and B, particular for agricultural products. So thank you. Submit your assignment and have a nice day.